All right, welcome to Rinkus Hines this afternoon. Unfortunately, there was a little scheduling snafu. David's not going to be here doing the IC stuff. I'm going to do a little presentation on subwoofer alignment with a full range system. Can you not hear me? Well, get the banana out of your ear.
Mic to zero. Mic to zero.
Check 1, 2. Is that any better?
Straight up is good. Trust me, it'll be fine.
Okay. Now it's killing me. All right. For aligning a subwoofer and full range system, one of the first things we need to know is where exactly, or I guess when exactly, is the energy arriving from the subwoofer system. It's pretty easy to tell when it's coming from the full range, but not from the subwoofer. So to investigate this a little bit, we're going to look at a perfect impulse response, which you're showing right here, and we're going to apply some low-pass and high-pass filters to those, similar to the response of a loudspeaker. You can model that with a filter. This is what the filters would look like in the frequency domain, and we're showing 1 kilohertz filters here to begin with. We'll slide down and look at very low frequency stuff in a little while. And you can see here's what the impulse response looks like in the time domain. Very pronounced peak for the high-pass filter, but the low-pass filter seems to be a little bit spread out in time. Next slide is going to show it zoomed in magnitude quite a bit, and you can now see a lot more detail. Now, since we had our initial impulse and we just applied some filters to it, the initial arrival time is still at t equals 0. There's been no delay of either one of these things. So the initial arrival of both the high pass and the low pass is right here at t equals 0. And that's contrasted rather vividly by the peak energy arrival, which happens about half a millisecond later for the low pass. So the key here is you want to look at the initial arrival energy from subwoofers, which is right here, and align to that, not align to the peak energy arrival. If we sum those two impulse responses, this is what we get in the time domain. In the frequency domain, it's just flat magnitude response, and we see the phase shift normal that we would get from some fourth order Linquist-Riley filters. Now, just for grins, we've delayed the high-pass filter to be coincident with the peak energy arrival from the low-pass. To do this, we applied just under half a millisecond of delay to the high-pass signal. And when you sum those two, you get a huge notch right at crossover. So this should be very clear that you do not want to align the peak energy arrival of the two. If you think about it, it really does make sense why this occurs. You've delayed the high-pass signal by almost half a millisecond. At 1 kilohertz, half a millisecond represents about 180 degrees of phase shift. So we put the two signals almost directly out of phase at crossover, and we get the big notch there as a result. Now we're going to slide down to 100 hertz. Still, the high pass has a very defined peak, but it's very hard to see the low pass response at all in the time domain. We've zoomed in between the purple markers here in the bottom graph, and you can see a little bit more detail there. And again, the initial arrival of energy is here right at t equals 0. It may be a little hard to tell exactly when it's coming up from 0 level, but certainly somewhere in this 0 to 1 millisecond range would put you in a lot better shape than putting it here at 4.5 milliseconds. Now, when we actually start measuring subwoofer systems and trying to discern exactly when the initial energy arrival is occurring, you'll get much better results if you allow as much high-frequency energy output from the subs as possible. Turn off any low-pass filters if possible, or put them to a very high frequency to allow as much HF out of the subs as possible. Of course, once you get all your delays set, you put them back in, and everything will still work properly. You can think about it kind of like sample rates. The higher frequency sample rate you use, the more time resolution you get. If you limit yourself to 100 hertz, you only have 10 milliseconds resolution. It's really hard to see when something is occurring with that coarse resolution. And this is shown somewhat graphically over here. You've got a little less than quarter wavelength of a 100 hertz sine wave, a 1K sine wave, and then a lot of cycles of a 20 kilohertz sine wave. And you can see also how the higher frequency components have a much faster rise time in the time domain. And this also contributes to what we'll see in just a minute. When we pull out all those high frequency components, that's what's responsible for this apparent gap in the energy arrival for the low-pass filter. It's not that there's a broadband time delay occurring pushing that low-pass out. It's that their high-frequency components are actually missing. If they were there, they'd fill in that area and show you quite clearly where the initial arrival of energy would be coming from. So let's set some time arrival goals for our system when we want to align them. Naturally, we want the energy from adjacent pass bands to arrive at the listener at the same time or as close as possible. There's several different scenarios used today, all ground stack systems, but there are various drawbacks for that, most notably coverage. You can have an all-flown system, which works very well, but sometimes it's not practical to do that for flying subs. We're going to look at a flown full-range system and ground stack subs. We're going to do that for two reasons. One, it's probably the most commonly seen configuration in use today, and it also represents the worst case for timing differences, so it's a good illustrative case for us. We're also going to set as a criterion, we want less than 2 dB of variation through the crossover region when we are finished with our alignment. To achieve that variation, the adjacent pass bands can't be out of phase by more than 75 degrees. Now for 100 hertz crossover, that 75 degrees corresponds to about 2 milliseconds of time offset. So as long as we keep everything to within 2 milliseconds of misalignment, we'll get no more than a 2 dB variation through crossover between our subs and our full range system. So we're going to look at an example system in a non-reflective room. We're just looking at direct field sound, nothing else. You see we've got an 8-box line array system here and 3 ground stack subs. And what I've done here is construct a map in ease looking at the difference in arrival times between the sub and the full range system. This can be very instructive to do and get you in the ballpark a lot more quickly in setting up your systems. You can see that for most of the audience area, you're about between 4 milliseconds and 8, 9, maybe 10 milliseconds out for most of the audience area. Now there's a couple of methods you can employ to get your delays set up. One is to start at the back and work forward. At the rear of the hall, you're going to have your shortest time arrival difference between the two systems. So we'll use that figure plus about our 2 milliseconds that we want to be within and apply that delay to the subs. So for this, that'll delay the subs about 6 milliseconds, and now we'll look at the new energy time arrival differences. In this area, we're in exact alignment. As we move forward, we go out of alignment, and as we move backwards, we go out of alignment. So you can see here that we've taken our 2 millisecond variation that we set as our criterion, and we've actually got, we've turned it into a plus or minus 2 millisecond variation. So now we've got a total of 4 millisecond variation to keep us within our 2 dB window that we wanted to maintain. And now we're going to look and see what that looks like as an SPL map. Same audience coverage area. Here we've got the flown array only, the full range array, and this is showing the coverage of the subs. Now no crossover filters have been applied at this point yet. But you can see in both cases you have very smooth, even coverage and a natural fall off towards the back of the audience area, just like you'd expect. Now in this map we see the subs and the array with our 4th order Linkwitz-Rayleigh crossover filters at 100 hertz. And you can notice in the middle areas we've got a huge amount of cancellation. Compare this to this, we've got about 9 dB of cancellation due to the misalignment and about 6 dB here. And in fact, if you notice this area, we've got 81 dB there. From the subs only, you've got 92 dB that the subs are putting out. So from the misalignment in this area, you've got about 11 dB of cancellation. Extremely less than ideal. So using the proposed alignment method, by delaying the subs 6 milliseconds, this is the coverage map that you'd have at 100 hertz. And you can see that now you've got the smooth, even roll off to the back of the house, much more uniform coverage, just like you'd expect. You can look at the frequency response at these various positions where I've denoted the SPL. You can see in the crossover region, very even. Since you're a lot closer to the subs than you are the full range system, that's why the level of the subwoofer in the low frequency range is much more exaggerated. As you move back, you've got very even coverage. Not even a dB of variation in the crossover region, but still a little closer to the sub, so it's showing hotter. As you move back, you're getting out of the region where we're at that 0 millisecond time arrival difference. So you've got about 1 dB of difference there in the crossover region. As you move back, the differences get a little bit more. And you can see as they're overlaid, you get very smooth, even coverage. If you wanted to, you could address this globally across the venue with an equalizer to flatten it out here. It would just give you a little bit hotter signal in the crossover region there. So that's the quick alignment method for subs. You just got to know what you're looking for in the time domain. And it's much easier to look for that in the time domain rather than looking at phase response or the group delay in the frequency domain. If you're doing FFTs and looking in the frequency domain, you've got to worry about reflections getting into your measurement that would corrupt the data. You can't put, you have to use long time windows to get that low frequency resolution, and you can't do that with short reflections. But if you keep everything in the time domain, all the reflections are happening way after the initial arrival of energy that you're after. So it's really better to use time domain.
So Charlie, what do you do? You go to the back of the hall and set that at about 2 milliseconds? Practical aspect, about 2 milliseconds in the back.
Yeah, let me get back to this slide here showing the arrival time differences. Well, if you you could set up, if you didn't want to actually map this, you could measure it. Yeah, set a mic back here, see what your time delay is, or your arrival difference in time delays, and use that plus that 2 milliseconds that we use as our maximum variation. In the back of the hall, you'll have maximum variation. If you want to, you can have perfect alignment back here, but then you'd go out of alignment as you move forward in this direction. And instead of having plus or minus 2 milliseconds, you're down to just plus 2 milliseconds or minus 2 milliseconds. If you have that exact alignment somewhere in the middle of the coverage area, you get maximum benefit and minimum difference in your frequency response when you start to sum.
So yeah, so at the back you set it so that what is it? The mid-high arrives 2 milliseconds before the sub.
Well, actually, in this case, the sub arrival happens first because your subs are on the deck, and your full range system's flown. So there's a greater path length difference from the system in the air to any point on the ground than there is from the subs on the ground. So you're actually going to need to delay your subs. I've got another method shown in here. I didn't know how much time I'd have, but got a couple of minutes. There's another method that you can use just to pick any place that you want to. If you want to have your perfect alignment, say where you've got a 5 millisecond difference initially, you can use that, and then you'll delay by that plus the 2 milliseconds. So you'll have to delay the subs for that amount, and then you're in perfect alignment there. But you see at the back of the hall, you're only out 1 millisecond. Where you'd be out 2 milliseconds is down here somewhere in the next room, so it doesn't do you any good. So you've sacrificed a little bit of that maximum area of maximum summation for choosing the area of exactly where you want to be in perfect alignment.
The end result in the back is the subs behind the mid-highs by 2 milliseconds, right? Your end result.
Yes. Yeah, as you go back here, your subs are going to be... Let me think about that for a second. Yeah, your subs are going to be arriving later here and earlier up on this side of that zero zone. Any other questions from anyone?
I think it's great, Charlie.
Okay, thank you for your attention.